Similar triangles. We've been talking about it all week. Can I get a volunteer to read out what's in this box up here at the top, starting with angle, angle? Go ahead, Azalea. Perfect. Thank you, Azalea. So, this angle similarity theorem. We can call it AA similarity theorem for short. As you move through your math classes, you're going to get more and more of these angle relationship theorems added. There's side angle side theorem. There's angle side, I forget. It's been a while. But for right now, we're just going to worry about angle. And this theorem states that if two angles of one triangle are congruent to two angles of another triangle, then the triangles are similar. Right? Exactly what we've been talking about the last couple of days. So let's take a look at this first example. Well, first and only example. While playing tennis, Matt is 12 meters away from the net, which is 1 meter high. Matt needs to hit the ball so that it just clears the net, which means it just goes over the net, and lands 6 meters past the net on the other side. So at what height should Matt hit this tennis ball? Anybody in here ever played tennis before? Ooh, a couple people. Good. Very nice. I used to play tennis myself. I was not good at it at all, but I tried my best, and that's all that matters. So when you're playing tennis, this is kind of like a side view of what we've got going on. This right here is the net. Okay, here's Matt right here. There he is. Okay, guys, please stop talking. Blake, stop talking. So we got to understand this image here first, right? Because there's a lot going on. Here's Matt. He's on one side of the tennis court. Here's the net right in the middle of the tennis court. And we could assume that his opponent, or whoever he's playing, is over here on the other side of the net, right? So we're looking at it from the side. Okay? Just trying to get an understanding. So, the distance between Matt and the net is 12 meters. That's this line right here. 12 meters. Right? And where he wants the ball to end up is right here. End point for the ball. The most important part about word problems, I've been saying this every time we have a word problem lesson, is we have to understand what's going on. If we can't picture this in our heads in the real world, it's not going to make any sense. So we need that ball to just go over the top of that net. And it needs to land 6 meters away from the net. Okay? The net itself is 1 meter tall. I'll do that in orange. The net itself is 1 meter tall. And what we need to find, what color is too yellow? What we need to find is X. How high up Matt should throw this ball for him to serve it so that it actually goes over the net. So just like our worksheet 76 that we talked about 10 minutes ago, we've got two similar triangles. We've got 4 side lengths. One of those side lengths is missing. So we can figure out what that length is by setting up a proportion. Okay? But before we set this proportion up, we have to prove that these triangles are similar. So we need to figure out which two angles are congruent within these triangles. Does anyone see one pair of congruent angles in these two triangles? Theo, you see a congruent pair? What's that first congruent pair?
90 degrees.
The 90 degrees, right? This little square in my smaller triangle and the little square in my larger triangle show us that we have two separate right angles. Those are both 90 degrees. Those are congruent to each other. Where's my other pair of congruent angles, though? Let's go ahead and break this up into two separate triangles so we can get a better look at what we've got. So my small triangle has a base of 6, has a height of 1, and we don't know what that hypotenuse is. All right, there's my small triangle, A, B, C. That's my small triangle. Now for my larger triangle, we don't know what the height is. We'll call it X. Yes. Yeah. I ran out of tissues, but there's paper towels by the door. So there's X. And we can draw our base here. Right? Now how long is the base of our second triangle? 12? 12 meters? That's a great assumption. Let's forget about this net for a second. Let's pretend that this net is not there. Look at that large triangle. Everyone see that? That big triangle? It's the whole thing. 12 represents the distance from the net to Matt. But we want the end point of this ball to be 6 meters away from that. You guys see what I mean? So the real base is not 12, it's 18. 12 plus 6, giving us 18. There's our hypotenuse and our right angle. Everybody take a look at that and make sure they understand exactly how we got this. Exactly. That's what we're going to have to do next. So both triangle, let's figure out, so we've got down here is angle D, up top is angle E, and at the point is angle A. So we know that the right angles are congruent, but what other pair of angles do we have here that's congruent?
A.
Angle A, why do you say angle A?
I don't know.
Well, what does angle A in the small triangle have in common with angle A in the large triangle? They're both green. Good. How about the fact that they're the exact same angle right here? Right? We could think of this image as two triangles overlapping each other. Like, let's see. Right? If this is our large triangle, just for a little visual example, this is our large triangle. The smaller triangle is right there. Right? Here's our smaller triangle. This angle right here is the exact same angle whether the small triangle's there or whether it's not. You guys see what I mean? So that angle, even though it's flipped around, you guys hopefully get what I mean. So this angle right down here, angle A, that's our second congruent angle pair. Angle A is congruent to angle A, just like if we had vertical angles. So both triangles contain angle A, and they contain a right angle. Therefore, triangle ABC and triangle ADE are similar, fill in that blank with similar, by the what? What rule tells us that these two are similar? It's in a box at the very top of this piece of paper. The AA similarity theorem. The angle-angle similarity theorem tells us that if we have two right angles and another pair of congruent angles, we have similar triangles. Now that we know for sure we have similar triangles, we can set up our proportion. So, let's do this bottom side matching up with this bottom side. We're going to do 6 over 18. Did you hear that outside, Jerry?
Huh?
Did you hear like banging outside? Okay, that's fine. So, everyone take a deep breath. It's all good. We're fine. I know some of us probably got a little bit nervous there. I did too.
About what?
The banging sounded kind of like shots. But it wasn't. We're fine. Everything's okay. But my heart kind of sank there just for a quick second. Hopefully everyone's all right. You didn't hear anything? Okay. I don't know. Maybe it was from another classroom. I don't know. But that was not fun. All right. Anyway. Oh, God. And we're recording this. Weird. So our first... at least we weren't recording with the actual camera like we have been the last couple days, right? That would have been an awkward piece to explain. So, sorry about that. Our first proportion, 6 over 18. Our second fraction's got to be 1 over x. Because 6 and 1 come from the same triangle, they've got to be directly in line with each other in the numerator. And 18 and x come from the same triangle, so they've got to be directly in line with each other in the denominator. Am I doing this right? Yeah. So we cross multiply. When we cross multiply, we see that we're doing 6 times x, and we're doing 18 times 1. So we're going to have 6x equals 18 times 1 just gives us 18, right? If we want to get x all by itself, we've got to divide both sides by 6. Cancels out, giving us x is equal to 18 divided by 6 gives us what? 3, right? Now, because we're talking about a real-world problem, we of course need units on this answer. So 3 what? What do we got 3 of? 3 meters, exactly. Now, we got to understand what this means, right? What does 3 meters mean in the context of this problem?
We need to put 3 meters in the air.
Exactly. If we go back to what we were looking for originally, we're looking for at what height should Matt hit the tennis ball. Matt's got to throw that tennis ball 3 meters in the air for it to precisely land 6 meters on the other side of the net. I'll scroll back down here to this. Questions I can answer about that. Perfect. That's all.